Hello and welcome to York Observatory's online astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. We are broadcasting live from the Alumni Carswell Observatory located at York University in Toronto, Ontario, Canada. York YouTube broadcasts every Wednesday night at 7:30 p.m. local Toronto time. For any questions or comments you have of our past shows, or if you have suggestions for future topics, please send us an email at observe@yorku.ca. You can always connect with us on Twitter or Instagram with the handle @York Observatory and Facebook at Alumni Carswell Ops. Good evening, everyone. I'm Maheen, and I'm one of your hosts this evening, along with Matt, Dhyan, Laur, and Sergiy. And we're here from the Alumni Carswell Observatory at York University. Tonight, we have a special guest joining us. It is York University's very own PhD candidate, Wen-Yi, who will give us a talk on the topic, The Quest for Mysterious Magnetic Monopole. Before we get started with our show, it is important to mention that the observatory at York campus is in Toronto, and we would like to welcome you all to our show and to acknowledge the traditional land that our telescope is on. The observatory acknowledges its presence on the traditional territory of many Indigenous nations. The area known as Toronto has been taken care by the Anishinaabe Nation, the Haudenosaunee Confederacy, the Huron-Wendat, and the Métis. It is now home to many Indigenous peoples. We acknowledge the current treaty holders, the Mississaugas of the Credit First Nation. Our stargazing and astronomical efforts join the long history and current practices of astronomy for this land. The observatory looks forward to continuing to learn and revitalizing our knowledge in this area. I will now hand it over to Matt for some astronomical updates.
Thank you so much, Maheen, and welcome everyone. Before we get started with our main show, we want to give you a little update on what you can see this coming week and specifically tonight. So this week we have Vega, we have Uranus, we have the Andromeda Galaxy, as well as the Pleiades. We have mentioned before in our nebulae Teletube that the Pleiades, also known as the Seven Sisters, is an open star cluster with a reflection nebula around it. But did you know that its name comes from the ancient Greek word plane, which means to sail, because of the presence of the cluster? The presence of the cluster in the sky was actually used to delimit the sailing season in the Mediterranean Sea. And they are also known as the Seven Sisters because their name, the Pleiades, was given to the seven daughters of Pleione in the Greek mythology. And I'm pretty sure you may know that the planets were also named after mythology. And in their case, it was the Roman version of the Greek gods. But the planet Uranus, as a matter of fact, actually refers to the Greek mythological god of the sky, Uranus, who's the father of Zeus, or Jupiter if we talk about planets, and the father of the Titan Kronos, or Saturn if we talk about planets again. And just like them, the Andromeda Galaxy, which will also be visible tonight and this week, is also named after a Greek mythological character, Andromeda, the wife of Perseus. Now, these names are related to real astronomical objects, but the mythology behind them is just a mere story or fiction. Now, talking about things that may not be just fiction, but more of a hypothetical thing, or in this case, a particle that could actually be real. Tonight we have an amazing presentation about something that still represents a challenge for scientists that try to prove its existence, but that one day, who knows, may be discovered after all. But before we hear about this amazing research and the particle behind this story, let's get to know a little bit more about our speaker tonight. So go ahead, Dhyan.
Thank you for the excellent update for the What's Up in the Sky, Matt. And now moving on to today's topic. We've known that for a long time that magnets always have two poles, the North Pole and the South Pole. And the idea of a magnetic monopole has been around for a long time, but we are yet to discover it. The idea of a magnetic particle with only a North Pole or a South Pole has been around for over a century. The discovery of this particle would not only reinstate the symmetry between electricity and magnetism, but it would also explain why charge is quantized. But how are we searching for magnetic monopoles, and how significant of a discovery of this magnitude be? Well, to discuss this electrifying topic, we are delighted to present York University's very own PhD candidate, Wen-Yi. But before we get into that, I'd like to tell you a little bit more about our speaker. She is a fourth-year PhD student working under the supervision of York University's very own Professor Taylor. She's also a member of the ATLAS experiment at the Large Hadron Collider at CERN in Geneva, Switzerland. She received her bachelor's degree in physics and mathematics from the University of Toronto in 2016, and her master's degree here at York with Professor Taylor on detector performance studies. Her current research is focused on searching for magnetic monopoles and other long-lived particles. Her most recent work, published on July 23rd, 2021, is on pair production of magnetic monopoles in stable high electric charge objects in proton-proton and heavy ion collisions. And now, without further ado, here's a special guest speaker for tonight, Wen-Yi.
Hello, let me try to get my slides shared. I hope you can all see my slide. So, hello everybody. It is a pleasure to be here tonight to talk to you a little bit about the magnetic monopole. This picture, as some of you may have seen, is a UFO sighting that came out some time ago from the US government. As weird as it may sound, the magnetic monopole actually shares things in common with an UFO. For starters, we have never seen a magnetic monopole or found an alien. In this sense, they're both unidentified objects, and we don't really understand them. Regardless of where you stand on UFOs, I hope I'll be able to get my point across by the end of this talk as to why some of us are so obsessed about the magnetic monopole. I'll also tell you a little bit about how it works to search for the magnetic monopoles in an experiment using the detector right behind me. The magnetic monopole is like an alien, but monopoles in general are not, because they are simply just charged particles. There are electrically charged particles like protons and electrons. So they're essentially electric monopoles, if you like. You can make them out of zero charge. Say if I have two objects that are made of different materials and neither has electric charge, if I rub them together, I'll end up with a transfer of electrons from one object to the other. Now, if I separate the two objects, one will have more protons than electrons, making it positively charged. The other will have more electrons, making it negatively charged. Now, if you try to do this with a magnet, this is not going to work. We know that a magnet has a south and a north pole and a zero magnetic charge. But no matter how many times you slice it, you will just end up with smaller and smaller magnets. Each of them will have its own north and south pole. So it doesn't seem likely that you can make a magnetic monopole with one magnetic pole and a net magnetic charge. These are the basic observations that established the basis of the theory of electromagnetism. On the one hand, we have electricity describing the interactions of electric charges like electrons and protons. On the other hand, the theory of magnetism describes the interactions or the behaviors of magnets. And this difference is the result of the absence of magnetic monopoles. When James Clerk Maxwell combined the two theories in 1973, he decided to leave magnetic monopoles out of the equation because he had never seen one, neither did anyone else. Oftentimes, when we talk about magnetic monopoles, We even dropped the word magnet from their names, and I'll probably do that as well for the rest of my talk, because electric monopoles have been named already. So why don't we just make a simple generalization for magnetic monopoles, at least for now? But the point is, in principle, magnetic monopoles could exist. Fast forward 60 years, in 1931, Paul Dirac came along and predicted the existence of magnetic monopoles. His argument was pretty interesting because it was the opposite of that idea of slicing magnets. What it is that if you take a magnet and instead of slice it into smaller and smaller magnets, imagine you could stretch it to make it infinitely long. If the two ends of the magnet become so far apart, they will look like two isolated magnetic monopoles. This construction gives rise to this so-called Dirac string, which is just the result of, the rest of the magnetic monopole the rest of the magnet that connects the two monopoles. Dirac argued that if this string is absolutely undetectable, then the magnetic monopole can exist. And the punchline is, how could the Dirac string be undetectable? The explanation Dirac came up with was brilliant. It was based on the idea that in general, the trajectory of a particle like an electron should be affected by the presence of a Dirac string. So we know if there is a Dirac string, then the electron's trajectory is going to change. However, this trajectory has a symmetry that depends on the charge of the magnetic monopole. If the magnetic charge is not an arbitrary number, but an integer value in units of this fundamental charge, GD, then the electron's trajectory will not be affected by the Dirac string. Thereby, the string is undetectable. This fundamental magnetic charge that Dirac defined is 68.5 times the charge of an electron. This relation not only predicts the magnetic charge of the monopole, it also explains why the electric charge is that weird number in some units of Coulomb if a monopole is found with this magnetic charge. On the other hand, the monopole mass is not determined by the theory. So in principle, a Dirac monopole can be as heavy as you want. Ever since the postulation of the Dirac monopole, many theories have been worked out to explain the possible existence of magnetic monopoles. There is one theory that I just have to tell you about. It has to do with the fundamental forces of nature and the way we perceive them. There are four fundamental forces. The electromagnetic force binds electrons to nuclei. The gravitational force makes the Earth orbit around the sun. The strong nuclear force binds protons and neutrons inside the nucleus. And the weak nuclear force converts protons to neutrons. These forces look like separate forces. However, the electromagnetic force and the weak nuclear force become one single force at an energy of about 1 TeV. You may not be very familiar with this unit of TeV because it is really not the energy scale we work with on a daily basis. TeV stands for tera electron volts, meaning a trillion electron volts. We know 1 electron volt as being the kinetic energy of an electron, the kinetic energy of an electron by accelerating through a 1 volt potential. 1 TeV, on the other hand, is the energy scale at high energy colliders, that are used for researches in particle physics. If you think 1 TeV is already extremely high energy, which it is, there are even higher energies. At about 1 trillion TeV, the electroweak force and the strong nuclear force unifies. This is a prediction of the grand unified theories. It turns out that all grand unified theories have magnetic monopoles built into them. But these gut monopoles are as heavy as the grand unification scale. So they're way too heavy to be produced in colliders. They can be produced in the early universe, so they're often surged in cosmic rays. But unless you're particularly obsessed about these gut monopoles, I think you can still have tons of fun searching for Dirac monopoles at high energy colliders, such as the CERN's Large Hadron Collider at Geneva, Switzerland. The Large Hadron Collider is a circular collider with a circumference of 27 kilometers. It runs protons in opposite directions close to the speed of light before they're made to collide at the centers of different detectors. There are 1 billion collisions per second happening at collision energies of 13 TeV. There are 4 main detectors deployed on the LHC ring. I will focus on the ATLAS detector, which is the one I'm involved with. ATLAS stands for a toroidal LHC apparatus. We can all quiz ourselves later to see if we remember this name. It has the shape of a cylinder. It's 46 meters down the cylindrical axis and 25 meters in diameter. It is the largest detector ever constructed for a collider. The idea of having a huge detector like this is to use it as a microscope to detect and measure particles created in the LHC collisions as they travel through the detector. There is this picture that I just cannot resist the temptation to show you. It is the ATLAS detector painted on a building. 100 meters directly below this building is the actual detector. Here is a link that you can follow if you would like to take a walk around the ATLAS detector, of course, virtually. Okay, on to searches for magnetic monopoles. ATLAS has a long-standing interest in these searches. It is the first LHC experiment that searched for monopoles using the earliest LHC data. So it set the baseline for all future LHC searches. This paper was published in 2012. Since then, ATLAS has published more results as the LHC collected more and more data with higher and higher collision energies. Here at York, Professor Taylor is leading the ATLAS effort. Currently, our team members are Anna Maria, Ethan, and also myself. For the rest of the talk, I would like to focus on how we prepare ourselves for a monopole search. So it is more of a search design instead of a complete recipe. Before we jump into collision data, the first thing we need to know is what are we trying to look for? Inside the LHC, the protons are set on the collision course. Then they collide in the center of the ATLAS detector. One way or another, monopoles are produced at the collision point and then scattered in different directions. We need to have models to predict how the monopoles are produced and how they travel in different directions. So now once we have these monopoles, we can focus on what they look like in our detector. This is important because we want to characterize their signals in the ATLAS detector. The signals come from the interaction of the monopoles with the detector material. When a monopole travels through the detector, it knocks off atomic electrons of the molecules of the detector material and loses kinetic energy. The energy loss of a monopole with one magnetic charge is equivalent to that of an ion with an electric charge of 68.5. This means the monopole will lose 4,700 times more kinetic energy than a proton. This is the most distinctive signature of the monopoles. So it is a crucial step to understand this difference. And this is also where we get to play with different techniques like machine learning to really answer the question, how a magnetic monopole is different from other particles in the collisions. Once we figure out what we're looking for, we should be able to take a look at the LHC data, right? Well, not really. There is still work to do because the data doesn't save itself. The collisions in the LHC, the Atlas detector, must be read out by a complex trigger system. What happens is that from the trigger system, the data gets moved to the CERN storage system. We access the storage when we analyze data. So trigger is really the name of the game. If a collision is not saved by the trigger, it's going to be gone forever. When we design our triggers, we need to make use of the information we learned when we try to understand the monopole interactions in the detector. And we use these information to make our trigger work the best. The trigger comes with two steps. The first step is a level 1 trigger. It uses hardware like electronics to keep the collision data on a time scale of nanosecond. The second trigger, or the second step, is the high-level trigger. It is a software-based trigger, and it operates at a much slower rate by refining the decision made at the level 1. Triggers are really not easy to design, but they're crucial if we wanted to do a search. As hard as the trigger may be, at least we have a lot of data to look at. This is the timescale of the entire LHC program, which spans 3 decades. We are right here. At the end of 2021, the next operation run is just around the corner. The data set we're currently looking at came from the run during 2015 and 2018. This is already a huge data set. It is 6 times more than the first data set collected between 2011 and 2012. However, we're getting double the data in the next run. But even this data set is only about 10% of the entire program. The restart of LHC next year marks the beginning of a new era, as it's on its way to provide us the largest data set for the next few decades. Of course, the Atlas search will benefit from this full data set as well. We will continue to play an important role in monopole searches. We are preparing for the upcoming run, so there is lots of room for people to join. We cannot say definitively if monopoles exist or not, as long as the search continues. But if I may quote Dirac, one would be surprised if nature had made no use of it. I guess I'll just stop here and take any questions you may have. Thank you.
Thank you to our guest speaker, Wen-Yi Song, for a very intriguing and amazing talk. It was great having you here. We will now move on towards some questions that our crew has for you. I'm gonna grab the screen share back. Handing it over to Dhyan.
That was actually a really interesting talk. One thing I'm confused about is the triggers. I don't exactly, could you explain the trigger part again? I don't exactly understand it. And then after, I have a question right here, but so my first question would be, So moving electric charges are responsible for the creation of magnetic fields, correct? So if a monopole was discovered, would this make magnetism a completely separate force? Or like how would it tie into electromagnetism?
That's a very good question. Well, if a magnetic monopole is ever found, it doesn't matter if it's a north pole or a south pole, we will have to modify the current understanding of the electromagnetism because the Maxwell's equations are going to be different. And I think we can also make use of the monopoles as a new source of energy, just as the electric energy.
Oh, that's actually interesting. And secondly, my second question would be, so far as we know, right, magnetic fields are loops that go out to that do not go out to infinity. So for, as you said, the Dirac string, it would extend out to infinity, right? So then the magnetic field lines, they wouldn't loop, would they? Because they would never meet, right? Like, and how would this affect electric charges is my question, I guess.
That's an interesting question. I don't think I have ever thought about it. I'm not sure I know the answer to it.
Okay, no worries. And could you just one more time explain the trigger part of your talk?
Yes. So these triggers are just a set of hardware electronics and software algorithms that we run in the detector to select data. And there are 1 billion collisions per second in the Atlas detector. And we cannot keep all of them. So we have to make choices. And the way we do that is to first use the level 1 trigger, which is a very fast trigger, to make a decision to see if there is anything interesting in the detector that makes the event worth keeping. And then once we save that event, the event is going to be passed to the level 2 trigger, where we run smart algorithms on the event to see if it's really what we are looking for. So it's a very complicated system. I agree. It's probably not very easy to understand.
Okay. So it's basically like cutting down the amount of data you get to only look at the good data that you collect out of like the billion collisions per second or whatever.
That's right.
Okay. Thank you. And I'll pass it on to Laur now. I think she has a couple of questions.
Hello. Absolutely amazing talk, first of all. But these questions were asked by Arfa about monopoles. The first one is, what if monopoles are created, but in friction of seconds, they find the opposite pole, and are they impossible to separate?
That's a very good question. That's actually, that object has another name. They are not called magnetic monopoles. If the monopoles are produced and then combined because they attract each other, those objects are called monopoliums. So there are magnetic monopoles that recombine after they're produced. And the magnetic monopoles we search for in the Atlas detector are specifically the ones that are that have high kinetic energies, so they can escape that potential when they're produced. Does that answer your question?
Yes, sorry, I was on mute. The next question is, can monopoles have smaller parts to it?
Can they have structures? I guess that's your question. So for the Dirac monopoles that we are considering here, they are point-like particles. That means they don't have internal structures. They're fundamental particles, if you like.
Okay, thank you so much. I'll pass it on over to Matt now.
Thank you, thank you. So, um, really interesting talk, by the way. My first question would be, what is the role of, in this case, the magnetic monopole in the study of high energy physics? What would you say it's the main role of?
Yeah, I think it's, so there are so many different types of magnetic monopoles. I'm only bringing up two types here in this talk. So I guess it's obvious that if a Dirac monopole is ever found, I guess so that'll be a big deal to the classical theory of electromagnetism. And I also mentioned this gut monopole. And if a gut monopole is ever detected, it will, I guess, because those gut monopoles are often searched in cosmic rays because we cannot produce them here, even at high energy colliders. So that will be that's a prediction of the grand unified theories. So I think that's one way to say that we at least confirmed part of the theory because the theory predicts monopoles and we found one. But even if we found a Dirac monopole and we've never seen a, let's say we don't see a gut monopole just yet, but we see a Dirac monopole, I think that's still important for grand unified theories, because that just gives us more confidence to believe that there could be monopoles, gut monopoles. They're just at an energy scale that's way too high to be produced here on Earth. And if we keep looking, maybe we will find one day in cosmic rays. So I guess the reason why magnetic monopole is so interesting is because it appears in so many different places and many different theories. And even if you see a monopole from that, even if you see one type of monopole, it probably tells you something about the other monopoles and the theories that predicted them.
That would be, it honestly sounds like a really big thing, a really big deal, right? Imagine like finding finally the magnetic monopole and what it would mean for all the theories behind it. And that also leads me to my other question, which is, what would you say are the main theories of how magnetic monopole may have been created in the early universe, and how does it relate to the theory of inflation?
Yeah, that's a very nice question. Again, I'm getting all of these questions, and I don't think I don't think I have the right answers to them. The theory of inflation, yes. So as I was talking about, to produce these gut monopoles, you need very high energies that probably only happened in the early universe. And I think the theory of inflation, the reason why we look around in the universe and we have never seen a monopole there, I think the only reason why that's the case is because the monopoles are diluted by the time we look at them, which is right now. Mm-hmm. And if we work backwards, we know that, well, we know there are many other particles in the universe. They're not as rare as a magnetic monopole. We have them around, but we don't have the monopoles around. So if we work backwards, we can probably calculate the evolution of the universe through the amount of magnetic monopoles we have in the universe, through detection using cosmic rays. So I think the discovery of a monopole in the universe will help us understand the evolution of the universe and also the theory of inflation, because inflation basically tells us that the amount of monopoles you have, the universe expands at different rates at different times. So that's something that also gets factored into the the amount of monopoles that we see today. I think these are all combined together. These are very nice questions.
Well, thank you so
again.
much, and your answer, I think it sort of gives me an idea of what this means, and why is it so hard to try and find this fascinating particle. But I think that there are more questions, and that's why I'll now hand it to Sergiy, who will be doing the last questions from the observatory staff. Thank you so much.
Thank you, Matt, for your insightful questions. Now, on to the last few questions. My first question is, can you only create magnetic monopoles in proton-proton collisions?
That's what we've been looking at so far. We have only been searching for magnetic monopoles in proton-proton collisions. But we also there are also studies out there that considered magnetic monopoles being produced in heavy ion collisions. LHC doesn't only collide proton and protons, they also collide heavy ions. So it will be a great opportunity for us during the next data taking period to look into the heavy ion collisions and see if we have a chance to produce monopoles and detect them in our detector.
While we're here, could you also answer some other questions I had besides the two that I made? Like, for example, why does splitting a bar magnet create two smaller bar magnets?
Right. If you cut a bar magnet in two, then so inside the magnets, there are, you can think of there are small domains inside of the magnets, and each of them is a magnet. They have a north and a south pole. So you cannot, so that's, and the magnetic field lines, if you like, inside of those small magnets is what makes up is what makes a small, even if you cut this bar magnet in two, you'll still end up with just smaller magnets because each of them has those small magnetic domains. I think that's the word we use, which has its own north and south pole.
I see it's magnetic domains. Thank you very much. My third question is, does the existence of magnetic monopoles affect the other fundamental forces and particles?
Right. So so far, we in the LHC in the Atlas searches for magnetic monopoles, we consider these magnetic monopoles are only since I'm looking at this standard model of elementary particles, we only consider the monopole interaction through electromagnetic force. So the discovery of a magnetic monopole, I think, will help us understand better how maybe they will affect the electromagnetic sector of the standard model. There are other monopoles being proposed, postulated in the other sectors of the standard model. For example, the strong interactions and the weak interactions. Are those interactions even labeled in here? Yes. So I'm not very familiar with the magnetic monopoles in those theories, but I think they will probably affect the theories in a similar way.
And my last question is, if with electric poles, we have protons for positives, electrons for negatives, and neutrons which are neutral. Is there a neutral monopole for magnetic monopoles as well?
A neutral monopole for a magnetic monopole. Can you say that again? I don't think I
like you mentioned, there were many different monopoles predicted by the theory. I was just wondering if it was possible that there was a neutral magnetic monopole.
neutral in charge or neutral in what?
So like we have a north monopole and a south monopole, analogous to the positive and negative of the electric monopoles. So I was wondering if there was an analogy to the neutron in magnetic monopoles.
That's an interesting question. I don't see why there shouldn't be.
I see. Thank you very much. And thank you very much for the answer to my question. And thank you very much, Wen-Yi, for the fascinating presentation. Well, everyone, you have been listening to LNI Carswell Observatory weekly Teletube broadcast, the Astronomy and Astrophysics program, written and presented by the students, faculty, alumni, and friends of York University. The hosts this evening have been Matt, Dhyan, Laur, who is voicing for Arfa, Maheen, and myself, Sergiy. Make sure to leave any comments or questions in the comment section of the video and talk to us in chat right now. We'll be around for the next 20 minutes to answer your questions. All of our programs are free, but if you'd like to make a donation, see our website at observatory.info.yorku.ca. You can always connect with us on Twitter with the handle @YorkObservatory and check out our website for show notes, content, updates, and contact info at observatory.info.yorku.ca. Thanks for tuning in, clear skies, and have a good night.